basically, this is part of my ongoing research work, my PhD research work, and it's being developed with my advisors, Professor Fernando Ramos, Professor Miguel Correia, and also Salvatore Signorello, all from the University of Lisbon. And basically, our motivation for this work is so we have recently there's an increasing sophistication of network attacks, and as many intrusion detection systems in production environments are yet signature based, they are unable to identify attacks that are previously unknown, that don't have any known signatures.
Sorry for the interruption. Can you zoom in your booster so we cannot see them clearly?
Of course.
So the text is small.
Okay, so
yeah, that's better.
Yes. So additionally, another type of attack which is becoming more and more common are short-lived attacks, and also attacks with very fast ramp-up times. And many, again, many needs in production environments often take several minutes to detect attacks, and this is not, and often fail because of this reason. And also the measurement primitives which are used in attack detection are often still based on packet sampling for scalability issues, and this approach is detrimental to detect intrusions. So our framework, our proposal is called SPEED, so switch powered intrusion detection, and we want to leverage the recent advances in programmable data planes that allow new monitoring techniques to be run directly on the network data plane, directly on the switches. And so basically, these programmable switches run a different set of measurement primitives and use a proactive approach to push these measurements to the monitoring system, to the control plane, whenever relevant changes in traffic occur. And these measurements are then fed as input features to a machine learning classifier to detect attacks as they occur. And through this proactive approach to attack detection, where the switch sends the measurements without waiting for a control plane to poll periodically, we aim to reduce the attack detection time. So that's the gist of it. And in terms of measurement of measurement primitives, we use not only traditional traffic statistics, traditional flow statistics, like the number of packets, bytes, source destination IP, the IP protocol, the traditional flow statistics, and we also rely on sketching algorithms. Sketches are probabilistic data structures that store information about streams of data. In this case, in our case, they allow an analysis on all packets at line rate without performing any kind of sampling, of packet sampling. And as these sketching algorithms are now able to be executed directly on the switches, we can use them to perform better measurements than using just the typical flow statistics. In terms of monitoring network-wide, an operator would configure switches with different measurement primitives. Each switch would be running different combinations of primitives according to the operator's needs, and these can be reconfigured at any moment during runtime without having to be restarted. regarding the evaluation of our system, we just performed a very preliminary evaluation, since our focus until now has been on data plane implementation. But so this evaluation was performed with an unsupervised machine learning algorithm, k-means, and we focused on 3 aspects, 2 of which are shown here. We have a detection speed, so we attempted to showcase that a push-driven approach, where the switches proactively sends measurements to the control plane, offers a much faster detection of ongoing attacks. And as you can see here, the speed detects the switch detects anomalous traffic patterns as soon as they happen in the data plane, and immediately sends them to the control plane, where they will be analyzed by the machine learning components to determine exactly what they are. Regarding the detection capabilities of our system, we tested them using 4 attacks. Here we show 2, and this the line in green shows our solution, shows a performance of that tests with speed, while the second line is also testing speed, but running only a single sketching algorithm instead of multiple. And the last line is a sampling based, netflow based solution, which uses only packet and byte counters from sampled packets. So from our tests, we concluded, we observed that speed consistently showed better results than the other 2, and in particular always showed a higher precision percentage than the other solutions. Now, these results are still very preliminary, and they show that our system doesn't still have the accuracy and precision which may be required by an intrusion detection system. But as this is a very, very rough machine learning pipeline, shall we say, and this will be developed at a later stage, this part of the work.
Okay, thanks a lot. Maybe I can ask a question. So I'm not an expert on machine learning, but I saw that you also use machine learning in this work. And normally in machine learning, actually you need to train the data, right? You need to train this model based on some data. So in your work, how did you do this training?
So this is so k-means is an unsupervised algorithm, so it doesn't require any prior training.
Mm-hmm.
But this is a question that we are currently thinking of, since the measurements that we send are only of anomalous patterns. The measurements that we send to the control plane are only of an anomalous patterns. We need to establish, shall we say, a baseline of regular traffic, so that the algorithm can determine what is regular and what is not. So what we are doing currently is from the traffic traces that we use to test the system, we are using regular traffic, which we know is not regular traffic, to serve as the bulk of the data. And then when we receive when the control plane receives an anomalous flow, anomalous pattern, it simply mixes it with the regular traffic.
I see. Okay, thanks a lot. Actually, I'm not sure if other participants in this session, I mean, do you have any questions or maybe you can just wait for the demo chair.
Hi, this is Vincenzo Mancuso. I'm still on time for a question or too late?
Yes, please.
Because I was looking I was actually jumping from one poster to another. That's why. I was curious about the name. You know that Speed in Italy is a system for security, which is basically some authentication service offered by public administration. And I mean, I don't know if you pronounce it Speed or Spied, but
It's Speed. I mean, yeah, we usually pronounce it Speed.
Speed, yeah, same thing in Italy, because it sounds like speed with double E, but it's actually something else. So what you're doing here, in which sense you can you have a switch powered? Where is the switch part?
Switch in the sense of a network switch.
Yeah, I understand, but so it's a programmable switch that you have, and you can do some kind of acceleration on the intrusion detection functions on the switch.
It's we mentioned switch powered in the sense that it's the switch that when we for the for the measurement collection, it's the switch is proactive. When the switch detects any anomalous traffic pattern, it immediately sends it to the control plane, instead of the traditional approach where the control plane periodically polls all the switches.
Just for curiosity, what kind of switch are you using? Because I know there are some Mellanox switches now, NVIDIA switches, that have some programmability features that allow to do what you are describing. Are you using them?
At the moment, we are still only using software-based switches. We have a Tofino switch at our university, and we are exploring an implementation on that switch. So a barefoot Tofino switch.
I see. Interesting. That could be very powerful. Have you evaluated what's the gain in terms of reactiveness, time that you save to detect an intrusion?
In an actual switch, not yet. That is an evaluation which we definitely want to perform at a later stage.
I see.
All the evaluations until now have been on software.
Mm-hmm. Well, I think there's a lot of work to do in this area, so I hope to see some papers of you around in the next year.
Thank you very much.
Thanks to you for presenting it. Okay. I think we are supposed to switch to second presentation. Is that correct?
Yes, Vincenzo, but we have 5 minutes in between.
Yeah, I remember, yeah.
So maybe I'll stop sharing now.
No, you can keep it, but I think Qing can switch whenever the other presenter is ready, maybe in a minute or two.
So maybe you can ask the second presenter to share his screen.
So okay, thanks, Qing. I will jump to a demo session now. I'll be back later.
Yes, I know. I know which session you are.
You know everything, yeah.
Yes, we have Skype. Huh?
Yeah, okay, you have informers. Okay, I see.
Okay, see you later.
See you later.
Jihun, are you there?
Oh, yes.
Jihun, yes. I think maybe you can start share your screen.
Oh, okay.
Yeah, because you will have 30 minutes for your poster.
Okay.
So I'll stop sharing now. So.
Yeah.
Okay.
So I'm starting at 5, right?
Yes, you still have 2 minutes.
Okay.
But I heard from other sessions that actually the poster chair doesn't want us to present our poster. We just need to wait for okay, he's here. Vincenzo, you're still here, right?
Me?
Vincenzo, the poster chair. No, I think he's not here. He left, okay. Because I just heard actually the poster chair doesn't want its presenter to present this poster if there are no audience.
So I think I will start right now.
Yes, go ahead.
Hello everyone, my name is Jihun. I'm an undergraduate student of cybersecurity major, Korea University, Sejong campus. Today, I'm going to talk about our research work co-worked with Dongwon Kim, Jinwoo Lee, Professor Heejun and Professor Wonjun Lee of Korea University, Annam campus. The title is Feasibility of Malware Traffic Analysis through TLS-Encrypted Flow Visualization. Due to personal reasons of the first author, I will present this work to you. In these days, with the increasing demand of end-to-end security, transport layer security protocol, in short, TLS, is being widely adopted for network traffic encryption. According to Google's transparency report, more than 95% of traffic across Google is TLS encrypted, and 80% of enterprise traffic on the Zscaler cloud in 2018 is SSL TLS encrypted. Encrypting traffic is essential for privacy and security of users, since malicious attackers can easily eavesdrop unencrypted traffic. However, the growth of TLS encrypted flows could disturb network monitoring and analysis for security purpose. According to an article from Sophos Labs, nearly a quarter of malware are now using TLS to communicate. Since the data of TLS encrypted flows cannot be monitored without secret keys, network monitoring cannot do anything for the flows. Especially traditional malware analysis approaches such as deep packet inspection, DPI, try to inspect malware's behavior by analyzing payload of TCP segments. But the approaches are no longer available. Although there are some alternatives for DPIs, for example, blind box, by inspecting directly on the encrypted payload, or HTTPS interception, but some of the proposals or not practical, and the others reduce security. On the other hand, there are several research efforts on malware traffic detection classification without TLS interception or inspecting encrypted payload. In 2016, Blake Anderson and David McGrew observed that features from TLS handshake metadata and related contextual flows can be utilized to classify TLS encrypted malicious flows accurately. Furthermore, another work from the same authors shows that L1 logistic classifiers with carefully chosen TLS flow can perform malware family classification with 90.3% of tenfold accuracy. However, these approaches require fine-grained feature selection conducted by experts. Furthermore, the above approaches need to conduct field-specific preprocessing for message field values. That is, understanding each field is essential to enable the approaches. To this end, we propose a coarse-grained feature selection approach for TLS flow metadata called TLS-Encrypted Flow Visualization. In our approach, we extract parts of several unencrypted TLS messages containing unencrypted metadata at the beginning of TLS flows, and we build the images by treating each byte as a pixel. Here is our image format. We colored the messages to distinguish each type for better visualization and added padding to cope with different message sizes of each byte. In our approach, we do not try to understand or utilize each field of the messages. Rather, only the bit pattern will be observed. Actually, our proposal is inspired by malware image visualization, which is widely used for malware binary analysis. Our approach has several advantages. At first, we utilize the common lesson from the previous research efforts. That is, TLS flow metadata exchanged at the beginning of TLS flow without encryption have fruitful information to classify encrypted malware traffic. It implies that we can perform early classification of malware family without monitoring the whole flow. However, different to the previous studies, we want to conduct the classification without detailed protocol knowledge. Second, images can capture small changes, yet retain the global message exchange pattern. It implies that malware variants in the same family could have similarity as images, and distinct patterns would be observed among different malware families. Third, we assign different color to each message type in TLS flow metadata. Therefore, different messages of a flow can be easily observed as a colored image. Although the coloring is ineffective for machine learning according to our preliminary results, it may be helpful for human. To show the feasibility of our approach in malware traffic analysis, we analyze images of several malware families. As you can see in the picture, we observe that different malware families have distinct image patterns. Note that each pixel gets brighter as it approaches 0x00. At glance, you may think that a distance measure such as Euclidean distance could be applied to the images for malware family classification. It can be true if all the malware images are like A, but unfortunately, there are some counterexamples like B, each of which tries to access to different websites. To this end, we try to conduct a machine learning-based classification to verify whether our approach can be usable for malware family classification. We applied two machine learning classifiers to the 1,358 TLS flows obtained from the malware traffic analysis.net website, where 70% of the flows are chosen for training a convolutional neural network model and a support vector machine model. Surprisingly, the CNN classifier shows 97% accuracy, and the SVM classifier shows 93% accuracy in total. It implies that the generated images are suitable for malware family classification, although this is a preliminary result. We have discussed the feasibility of malware traffic analysis through TLS-encrypted flow visualization. We observed that different malware families have different patterns in their images, but another kind of differences could be available in the same malware family. Surprisingly, malware family classification via images using SVM and CNN models has high accuracy. As you can see in the result, although the images of the same malware family do not have same pattern, it can be seen that each malware family has distinct characteristics. In future work, we will further discuss why such high accuracy could be possible. Thank you for your attention.
Okay, thank you, Jihun. Still, I don't think we have other participants, right? We don't need participants, huh? So maybe you can just wait a bit. Huh?
Oh, okay.
I mean, again, I'm not a session chair. I'm also a presenter. I just host the session.
Oh, yes.
Hi, Jihun, do you
Yes.
hear me well? Okay,
Yeah.
I just asked a question in the session's Q&A. Would it be possible that you posted, I don't know if the work came from a paper that you guys did some time ago, but I would really enjoy to read it if it would be possible.
Oh, the paper?
Yep.
Huang, you mean this paper, right?
Yes.
Actually, you can download the paper from the RCMP website, the official website. I can send you the link.
Oh, that would be great. If you can paste it, you can copy that here in chat on the session Q&A.
Yeah.
So not in this Whova thing, but in the ICMP 2020?
Yeah, ICMP post, I will send you the...
So it's the ICMP 2020. Because I thought everything was already here.
Yeah, I already posted the links there. You can just find these papers, and you can find all the PDF of all the papers accepted to RCMP and also the workshop papers.
All right, you posted the link
in the chat. Yeah, in the chat. You cannot see the chat, right?
I don't know if I'm seeing the chat.
Wait for a moment. I can post to the
no, got it. Yeah, I got it now. The program. You pushed the program, yes.
Yes, program, yeah. This security.
Today is the 15th. This is security. Yes, thank you very much. Thank you.
Welcome. Actually, I cannot see the chat because I posted the link in Zoom, but again, I just posted it again in Huo. Jihun, maybe I can ask a question about your last conclusion. You mentioned
Okay.
that both SVM and the CNN, they have a very high accuracy. I mean, even though the images, they don't have similar patterns. Actually, I'm wondering, I mean, if it is possible that you can judge from the patterns in the images to see, I mean, which one will give you a high accuracy. Is that possible? And also, I believe that there are also maybe other possible solutions except for SVM or maybe CNN, right? I mean, if you have the corresponding images, can you just tell from the images and see maybe which one will give you a high accuracy, which one maybe not?
The images?
Yes.
Something like this.
Yes, yes. Can you speak? I'm wondering, I mean, if we as human beings, if we look at the images, can we tell, I mean, which one will give us high accuracy? I mean, if we use a CNN, maybe we also use other SVM, right? No, or maybe I didn't follow this paper. I didn't follow because I'm not an expert here. So.
Can you then chat?
It's never mind. Because in your last conclusion, you mentioned that, I mean, even the images, I mean, the patterns in images are different, right?
Yeah.
But I mean, with your two proposed CNN and the other method, and both of these two methods actually give you a very high accuracy. Actually, I'm wondering, I mean, the relation between your proposed method and the patterns in the images. Are there any relationship between these two, or any insights in these two? I mean, basically your last
CNN and SVM.
Yes.
There are both two relationships.
Mm-hmm.
This is the you know, CNN and SVM. You know the meaning of CNN and SVM.
Mm-hmm.
So you want to know why we used it?
Maybe I can ask another question. So here you can see that actually the performance of a CNN is better than the other one, right? I mean, the accuracy is higher.
Yeah.
Yeah. So do you know why?
I don't know the real reason, but I think most people use CNN in image like this.
Mm-hmm.
Yeah, and image like this to CNN.
Mm-hmm.
So I don't know the real reason, but there must be. It always shows high accuracy on CNN with this picture, I think. So people use things like that. We colored this image, but it is usually a grayscale image. And people use CNN with grayscale image. So I think there is reason
Okay.
for why they use it.
Okay. And do you know if, I mean, CNN is always better than the other one, than the SVM? I mean,
Always.
Always, right?
Always better.
Always better than the other one. Okay. Yeah, because I'm just wondering about this. Because I'm not an expert on machine learning. I only have very little knowledge about it. Okay, that's good. And also, I mean, do you know the physical layer security?
Sorry, pardon?
Do you know have you ever heard the physical layer security in wireless communication networks?
Yes.
Yeah, because I think they also want to try to, let's say, to detect or maybe protect the signals in the physical layer. And also they only look at the signals. I'm not sure if there's any similarities between, I mean, physical layer security and your, because the TLS is transportation layer security, right?
Oh, yes.
Okay, okay, okay. Yeah, I mean, just wondering, I mean, are there any, let's say, connections between these two?
Connections?
Yeah, between the physical layer security and the transport layer security. I'm just wondering about this. Huh? So you can ignore the question.
Oh.
Or maybe you can go to your slides 5.
5?
Yeah, slides 5.
Yeah.
I see here on the bottom, I mean, under the server key exchange, you have 25 bytes. Actually,
Server keys.
yeah. Server key exchange, you have 25 bytes. Actually, I didn't follow why on the y-axis you have, let's say, 4 bytes, 6 bytes, 4 bytes, 14 bytes, 14
So
bytes.
you want to know why these sizes are different?
Yeah, yes.
Yes. It's because its average size of its client hello and client key exchange and server hello certificate server key exchange, it's all different. Its average size is different. So we used the average size of client hello and client key exchange and server hello certificate server key exchange. So it's different.
And for the client hello, how many bytes do you have? You have 4 times 25 bytes, right?
Yeah.
So the 4 bytes is something. Okay, I see.
Okay.
Jihun, I think you can stop share your screen. You are already finished your time slot.
Okay.
Okay, so I will share mine. Okay, I think I can also start. Jihun, can you hear me?
Yes, we can hear you.
Okay. So I can start. So hello everyone, welcome to my presentation. So my name is Jinwoo from Delft, the Netherlands. I am presenting our poster on securing IoT through coverage bonding wireless communication with visible light. This is a joint work with Jona, David, and Sofie from Leuven, Belgium. I believe we all agree that our reliance on wireless communication has significantly increased in the past 2 decades, with either revolution or evolution of mobile networks from 1G to 6G. Now we are exploiting the millimeter frequency band for 5G and beyond, and also have also started the 6G network to meet the ever-increased demand for wireless capacity. However, when we use a higher frequency, waves such as millimeter wave for wireless communications, we are facing several problems such as the high complexity of antenna design and the signal processing. Therefore, people were looking for new frequency band that has large bandwidth but needs simpler design. So one of the possibilities is using the visible light frequency band. Compared to the radio frequency communication, wireless communication with visible light has several advantages. The bandwidth is much higher, the signal processing is easier, the devices are cheaper, and also we have a lot of lights in our life. And more important, visible light communication is secure because we can easily bound the communication range into a room through something like walls. So in this poster, we propose Hodal to make a step further, a coverage bounding wireless communication system to secure the Internet of Things. The potential IoT attacks would only occur in the delimited area. Here, the coverage bounding means the communication coverage is controlled accurately in 3D dimensions. Visual implies that the communication coverage and process are visible to users, representing an important and user-friendly side channel for securing IoT. Hodal can provide secure wireless communication both psychologically and technically, which means nodes can only communicate with each other within the delimited area. It can benefit IoT applications for secure wireless communications, especially those that demand secure interactions in proximity. Let us look at an example. In this figure illustrates the proposed coverage bounding and visual wireless communication. In this figure, Bob can talk to Alice. Chunk cannot talk to Alice because it is out of the range which is delimited by Alice. Therefore, Alice can easily prevent the attacks from Chunk. Similarly, in this figure, an attack from Eve through non-line signed links is physically prevented by Alice's bounded communication average with surrounding obstacles such as the walls shown here. Besides, the communication medium is visible light. Therefore, Alice and Bob can see the communication coverage. Thanks to this coverage bounding wireless communication, potential attacks from the nodes such as Chunk and Eve can be prevented. Consequently, attacks and even privacy links of the network could be reduced greatly. Vincenzo, I see you're here. Do you have any questions?
No, I'm trying to understand what you're doing. So I was watching. It's okay. Please explain us what you're doing. So
okay.
Then I have my questions.
Okay. So to realize Hodal, we propose two types of preliminary methods, physical methods and software-defined methods. In the physical methods, we explore the physical properties of nodes and the surroundings. For example, we can use a lens or an opaque cover to control the field of view LEDs at the transmitters. Similarly, such as shown here. Similarly, we can also use an opaque cover at the photodiode of the receiver to only receive the light signal from the bounded directions. Furthermore, visible light cannot penetrate opaque materials. Therefore, surrounding environment such as walls, cabinets, and curtain can be leveraged to physically bound the wireless communication area. These methods are similar to the isolated servers in which network interfaces are all blocked to prevent all the attacks from the internet. Another type of method is software-defined. They can dynamically change the parameters, settings at the transmitters, receivers, or even the environment. We could control several neighboring LEDs to transmit constructive or destructive visible light signals to bound the communication areas. If some LEDs modulate the light to interface with the surrounding visible light signals, such as in a destructive manner, then we can shrink, we can reduce the communication coverage. We can also even create specific shapes of the bounded communication area that cannot be achieved with a single LED. Another method shown here is to program the environment.
Qing, how fast can you switch?
You mean the switch LED, right?
Yeah.
Yeah, for that one, actually, it depends on which kind of LED we use. We can switch it maybe on a million times per second. That's also possible. That's possible.
Million, you said. Wow.
Yeah, it's mega.
Okay.
Yeah, millions, yes.
But
I mean, just like the visible light communication.
I mean, if you have to decide, if you have to make a decision on how to switch, what you have behind? You have some computation to run. Is that so light? I thought it was more heavy and took more time just for computation to decide how to switch.
Yeah, because if you want to interface with other visible light communication links, you can just blink the lights at a very high frequency. Then you can already interface with the ongoing visible light communications from other LEDs. But of course, I mean, if we want to use some other methods, such as let's say a transparent or maybe smart window, let's say smart glass, and then for this one we cannot control these smart materials at a very high speed. Then the speed here is much lower.
But that's because of the technology of the material itself.
Yeah,
because
yes.
I mean, it's just the inertia of the material or thing like that.
Yes, the limitation is there. Actually, for this one is quite similar to the metal surface, which is studied for FCG at this moment.
Yeah, but that's completely electronic. So that one I think is much faster because they managed to do it in a digital way, not by moving.
Yeah. Yes, that's right.
Okay.
Yeah. Actually, here in our group, actually one of the professors in our group, he is also studying this direction, and they found that actually because previously, if we want to use LCD, we can only control it, let's say, at maybe 1,000 times per second. And recently, they found another method to increase the speed of controlling the LCD at much faster speed.
Great.
Much faster. Yeah. Should I continue?
Yeah. Well, so I'm curious to see if you have a real piece of device actually.
No. Actually, we have some test. We have some results based on test pattern. For example, here, but here we only use, because here we have 3 LEDs here. We use the transmit 8 to transmit the regular visible light communication signal, and we use 2 other LEDs. These 2 in red to transmit the interfering lights, and we can see here, based on the transmission power from these interfering LEDs, we can control the communication range into different areas.
Right, quite precise.
This is the only result we have based on experiments.
Great, looks wonderful. Huh?
Kind of. And also, but of course, we also have some simulation results as shown here, where we have 4 transmitters here. We also have some blockage, such as human bodies, and also a cabinet. This is across the cabinet, and based on this blockage, actually, we can also, and also based on the interference from other transmitters, we can also bound the wireless communication range to some specific shape. And similar here, we just use a curtain to to block or unblock the light. Yeah, but of course, I mean, for this one, we cannot dynamically control these blockages. But for example, if we replace this curtain with smart glasses, or maybe this cabinet with smart glasses, actually we can control them dynamically based on the communication needs from the ongoing communication links.
Yeah, but then it's like you want to force the environment around what you want to do. Isn't it a bit too heavy and expensive? I mean, if I
Yes,
if I
yes,
have a
yes.
network with a few antennas and maybe get half of the power, half of the rate, I may be happy if I don't have to spend thousands of euros to build new walls and glasses and whatever.
Yes, actually, that's a good point. But if you look into the current research, also in other wireless communication area, people, I think there are already a lot of study on the transmitter side, on the let's say infrastructure, on the receiver. That's why people know that they want to program the environment. But I agree with you that I mean the cost will be very heavy. But remember that actually with visible communication, we can also use the light from the lasers. And there, actually, the beams are much narrower, and can also, I mean, if we use a laser instead of LEDs, actually we can control the bounded communication range more accurately and also at a low cost. That's our next step.
Nice.
Yeah.
Okay, thanks, Chinga. I will have to jump to the demo, otherwise I will not catch the last presenter. But thank you. You keep producing great jobs. Great, you do great work as when we were in the same institute.
Thanks a lot, Vincent.
Okay,
See you.
I'll see you.
See you. So as I mentioned before, we have two different methods. One is the physical methods, and the other one is the software-defined methods. And in the physical methods, basically we change the environment physically. We can use a cover at the transmitter. We can use a cover at the receiver to bound the, I mean, where the light should go. And another method is software-defined methods. As I just mentioned, we can control, let's say, the different number of transmitters. And also we can control the environment, such as programming the, let's say, the window or the smart window to help bound the wireless communication range. And these are just some simulation results. And we can see here, I mean, with the physical methods, with the human body, with inference, actually this is software-defined method, with the inference from a neighboring LED, and also with the help of a cabinet, actually we can bound the wireless communication range accurately. Similarly here, we add another curtain to help us bound the wireless communication range. And similarly here, this is the results based using the software-defined methods. We just use we use 3 here. For this one, actually, we only have this transmitter 1 transmitting. And in the middle, we use transmitter 2, 3, and 4. They all transmit interfering signals. That's why actually we can bound these coverage like this one. And on the right figure, we increase the transmission range into a rectangle. And basically, from these two, we can see that actually we can change the size of the bounded area. Yeah, this is just the results we have from experiments. This is a dense real CTS space we built in Leuven, and based on this dense real CTS space, we test our proposed coverage bonding wireless communication technique, and we can see the results, which is quite similar to the result we got in the simulation. And this is just the conclusion. So in this poster, we proposed the concept of coverage bonding wireless communication technique, or maybe concept. And we proposed 2 categories of preliminary methods to bound the wireless communication range. And also finally, we evaluate the proposed concept in both the simulation and the experiments. Yeah, that's all. Thank you. I mean, if you have any questions, just